In this video, we will look at shared state. The state of a program or script refers to the data stored in memory. The data consists of a set of variables with assigned values. As the program executes, the state will change. For example, procedures may add, delete, or modify data in memory. The concept of mutable state refers to data in memory that can be changed by procedures. In contrast, immutable state refers to data in memory that cannot be changed. With immutable state, the data can be created. Then, once created, it can never be changed. But it can still be copied, and then changed. Some variables in memory have simple data types, while others have complex data types. The simple data types are usually immutable, while complex data types are usually mutable. For example, let's say you have a variable that stores a number. Since it is a simple data type, the variable will be immutable. When you need to change the value, a new variable actually gets created in memory. And a new value gets assigned to that variable. Sharing immutable state is not an issue. Two procedures could be simultaneously reading the values of a set of immutable variables. Since their values are immutable, each procedure can be sure that the other procedure will not suddenly change one of the values. However, sharing mutable state is more problematic. In the example, two functions have been defined, each changing the state of a shared dictionary. A dictionary is a general-purpose data structure for storing a group of objects. In this case, the example is very simple and still easy to follow. However, when many functions are all updating the same shared mutable data, understanding the interdependencies becomes difficult. And bugs are likely to appear. Next, let's look at how this relates to the data flow approach to software development. With the data flow approach, a program is defined as a directed graph of the data flowing between procedures. Note that we are not specifically referring to the flowchart in Mobius. Theoretically, if the flowchart splits into parallel branches, then procedures can execute concurrently. This raises some issues with regards to shared mutable state. If the data flowing through the graph has a complex data type, then certain issues may arise. Parallel nodes can be modifying the shared data at the same time, resulting in unpredictable results. For example, consider these two procedures. Each procedure can change the data inside the dictionary. One procedure changes the value of variable a to 11. The other procedure changes it to 12. The final value is now unpredictable, as it depends on which procedure got executed last. One way to avoid conflicts is to make the data immutable. In the example, each procedure can read the input data, but cannot change it. Each procedure creates its own data. The final output of the data flow then includes all three datasets. The downside of this approach is that it can be very inefficient. For example, if we consider procedures working on a complex 3D model, each procedure would have to keep duplicating parts of the model. If the data is assumed to be mutable, then a different solution is required. The solution used by most data flow systems is to copy that data. This is sometimes referred to as defensive copying. Once the data is copied, it no longer shared. In the example, each procedure gets its own copy of the data. Each procedure can now update the values inside the dictionary independently from one another. If defensive copying is used, then the next issue is what happens when the copied data needs to be merged. When merging, conflicts may need to be resolved between data items with the same name. In the example, we have two data items called A, and they have different values. This is a conflict. Different dataflow systems may handle this in different ways. One approach is to automatically rename data items to avoid conflicts. It is then up to the user to decide how to handle the renamed data. For example, with a dictionary, one approach would be to merge the two dictionaries, but to rename the keys so that the two sets of data do not overwrite each other. The downside of this approach is that it is more complex for the user. They must manage duplicate datasets. Another approach is to raise an error when a conflict arises. It is then up to the user to fix the procedure to avoid the conflict. For example, we can see that procedure A modified the data, but procedure B created some new data with a different name. Every now and then the user may get an error, but this approach has the advantage that it avoids generating any duplicate data. This makes it more efficient. In general, creating multiple procedures that modify the same data should be avoided. Typically, each procedure should be modifying or generating different data sets. In the example, we can see that the two procedures are producing different datasets. As long as the dictionary keys are mutually exclusive, no conflicts will arise. Note also that these issues only arise with parallel dataflow patterns. With linear dataflow patterns, there is no need to make any distinction between mutable and immutable data.